Hi, welcome to this video. In this video I'm going to explain something about the USB I/O expander project that I created, which is programmed to the YAL programming language. So what will be the contents of this video? First, something about the project. Then the features of the USB I/O expander. Then about the protocol that I'm using to control this device. And an example of controlling the USB I/O expander using a terminal emulator. Then the basic schematic diagram that I'm using for this video and all the demonstrations. Something about the PIC software. The support tools that are available. Of course, a demonstration video showing all the functionality. And at the end you can find some references. So I created this project so that it could control pins and special devices with I2C or SPI interfaces by using a PC and only using commands that I could enter as ASCII characters. So there's no need for programming, so it makes life easier. And I have some Python examples which can be used for demonstrating and testing purposes, and this will make life even more easier. And there's complete documentation on how to use this device. And it's also open source. And at the end of this video you can find a link to the references. So what are the features of this USB I/O expander? When you connect it to the PC, the device behaves like a COM port, and you can send commands and data as ASCII characters. And the functions are reading and writing 8 I/O pins. You can control an IC via an I2C interface or via an SPI interface. There's a digital to analog conversion channel, 2 selectable outputs, and there's an analog to digital conversion functionality, and you can select one of 4 analog inputs. And there are 2 2-channel pulsive modulating signal generator outputs. There's also a reset and a ping command available, but I recommend not to use the reset because then the device disconnects for a short time, but the ping command can be used to check if the device is still alive. So if you look at this protocol, a command uses the following syntax. It starts with an exclamation mark followed by a command, data and carries it to a line feed. And all data must be given in ASCII hexadecimal format. And spaces are ignored, and also command and data are case insensitive. When you request for data, then the format is as follows. It starts with a question mark followed by the data you requested and the carries it to a line feed. And all data is returned in hexadecimal format. There are no spaces between the various bytes. If you have given a command and it's executed successfully, then you get the 0 as a response. Or, in case of an error in the command or its parameters, you get a 1. And response 2 means the command is unknown. For example, if I want to read from an I2C device with slave address AE and I want to read 10 bytes, then this is the format. So it starts with an exclamation mark, IICR for reading, slave address and the 10 bytes. The response will be 0, which means OK. And the answer is then the 10 bytes that you have requested. So it starts with the question mark followed by 10 bytes. And here is an example. This example is an EEPROM memory that can be controlled via I2C, and it has a starting slave address and a starting address where you want to read or write. And the starting address is a word address. So we start with a ping, and then the response is 0. Then we need to initialize the I2C interface, which is IICI, and the 4 means 400 kilohertz. Then I'm going to write to the device the first start address, which is a word address, so 2 bytes, 2 times 0. And then I want to read IICR 10 bytes from this memory device, and it returns 10 times FF. The next instruction is to write 10 bytes of data starting at address 0. Then if I want to read it back, I have to first set the start address to 0 and then request IACR to read 10 bytes, and then the 10 bytes that I have written are returned. So the basic schematic diagram is very simple. It's just one PIC connected directly to the USB bus. So on the right side you see the 8 pins numbered from 0 to 7, and the connector is just as a reference, but you can connect it to anything that you want. So the PIC software, it's about 7K in ROM size and 400 bytes of RAM, and the PIC that I'm using is 16F1455, which has USB capabilities. And the PIC itself has 8 kilobytes of ROM and 1 kilobyte of RAM. And the main program handles all the commands and sends all the data. And all other functionality is available in include files, which makes maintenance easier. And I did not write all software myself. I'm using various YAL libraries, for example the libraries for I2C, SPI, the DAC, the ADC and the PWM. So you can easily operate the device without any tools. You just need a terminal emulation program and you can type some ASCII commands. And as I mentioned before, there is a manual which describes all the commands and the responses. And there's a Python library which is available to make life easier, and there are also some Python example files available that I have been using for testing, but I'm also using them in this video for demonstration. So as a demonstration I will show each feature using different hardware which is connected to the device. I will also show the schematic diagram that I'm using for this specific video before the demo starts. And I'm using the Python example file which I also use to test the device. So the first video is to control the pin as outputs. So I added some resistors and 8 LEDs to the output ports of this device. So here I have my Python script and also my Python library, which is called the USB I/O expander, which provides all kind of functionality to make life easier. And this is the test pins output script that I created. So what you normally do, you import the required functions from the USB I/O expander, and each script has a main part in which it uses a default COM port, but if you provide arguments it will use that COM port, and then it will initialize the COM port. And then it starts with in this case with the pin functionality. So we start with setting all pins to output, we switch the pins low, and then there's an endless program in which we set all pins high, all pins low, and then each individual pin high and low. And each function returns true if the command was successful, and if it's false then you get an error message. So I will now run this program, and as you can see the LEDs are turned on and off, and also the individual LEDs are turned on and off. And you can also see here what the program is doing. Using the control pins as input, and in this case I added pull-up resistors to the inputs because otherwise they're floating, and I'm using a wire which is connected to ground to make each pin low for a certain amount of time. So this is the test of the pins, but then we use them as inputs. So we start, all pins are connected to the VCC via a pull-up resistor. So first I'm setting the pin direction to input because of course I want to read the pins. And here I enable, there are 2 pins that have a weak pull-up resistors. I enable them, but it's not really needed because there are already pull-up resistors. Then there are 4 inputs that can be set to analog, so we need to set them to digital. These are pins 0, 1, 2, 3 and 6. And then we run the test. So first we get the status of all the pins by reading the port, and then we get the status of each individual pin, and this is repeated continuously. So let's run this one. So what you see is the port state is FFFF because all pins are high, and now I will make each pin low individually. So I start with the least significant bit. Oops, so. And then the next one, bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, and bit 7. And control an I/O expander via I2C. So the USB I/O expander is connected to a separate I/O expander which can control 8 outputs or 8 inputs. And the communication is via I2C, so there are 2 pull-up resistors. So we start by initializing the I2C interface with a frequency of 400 kHz. Then on the I/O expander I will set all pins to output. The next step is that I set all pins to high, so the LEDs will be turned on, and then I will set all pins to low. Then the program continues with an endless loop in which I will put one LED high or one pin high in the port register. I will read the value back from the latch register, because you always should read back from the latch if you don't want to use the ports as input. And then the next LED will be turned on. When it reaches the end, then it goes the other way around. So I start with the most significant bit and move it back to the least significant bit. So let's run this program. Controlling an I/O expander via the SPI interface. This is a chip of the same family, but instead of the I2C interface it has an SPI interface. So this demonstration will show the functionality of the SPI interface. And you may wonder if you have a déjà vu, because I have connected again an 8-bit I/O expander to this USB I/O expander, only now one with an SPI interface. So we start by initializing the SPI interface with a certain mode and clock, which you can find in the manual. And then we need a chip select pin. So one pin is needed to activate the device. So we have selected pin 3, which will be set to output and will be a digital pin. And then we can actually access the device by first selecting the device, writing some data, and then deselecting the device. And in this case we have set all pins to output. Then we will make all outputs high, all outputs low, and then the program continues as in the I2C program by making one pin high and moving it to the next pin. We will also read back the data that we have written, and when the most significant LED is on, we will turn it around and move it back to the least significant LED. So let's run this program. Controlling the ADC. For this I'm using a potentiometer which I connected to one of the analog inputs. When I change the position of the potentiometer, you will see the changing values on the screen. The next demo is the demonstration of the analog to digital converter. So we start by initializing the analog to digital converter with a selected channel. In this case it is channel 4. Then we will enable the ADC, and then we will show continuously the value of the ADC. And there is a potentiometer connected to the board, and I will turn the potentiometer so that you can see the change in the value. So let's run this program. So I will lower the voltage on the input, and I will make it higher to the maximum. And lower it again. Controlling the DAC. In this demo I'm writing different values to the DAC, and the output of the DAC is measured using a multimeter. The next test demonstrates the functionality of the digital to analog converter. So we start by initializing the DAC. The selected DAC is set to 1, so we're actually using the first digital to analog converter. Then we will enable the DAC, and then the following program continues. First is we're setting the DAC to the minimum value, then we're setting the DAC to the maximum value, and then we increase the DAC value from minimum to maximum in small steps. So you can see the results on the multimeter, and let's run this program. Controlling the PWM. In this demo I'm creating two PWM output signals with the same frequency but with different duty cycles, and the signal is shown on an oscilloscope. So this video shows the PWM functionality. I will initialize the two PWM outputs, so start with PWM1, PWM2, then I will enable both outputs, and then I will change the frequency on both outputs. The frequency on both channels is the same, but what you can change is the duty cycle. So we start with a minimum frequency of 750 Hz, and I will, for channel 1, I will start with the lowest duty cycle and will increase until its maximum. And for channel 2 I will start at 100% duty cycle and will decrease until the lowest value. And after one round the frequency will increase with 250 Hz, and the maximum frequency is 45 kHz. So let's run this program. Of course this will take some time, but I can stop the program, and what you will see is that it keeps on running with the latest, let's say latest PWM frequency and duty cycle. So I will stop it, and still the signal is there. You can find all the YAL sources for this project on GitHub, including the hardware schematic and the documentation. And if you want to know more about YAL and about the YAL programming language, you can visit the YAL website. And if you have questions on how to use YAL, there's a very good YALib tutorial which you can download from the website. And you can also visit the YAL's Google group to post your question. For reporting bugs in the YAL libraries or in the YAL compiler, or for special requests, you can visit the YALib Google group. And all the YAL sources, including all the tools and the compiler, can be found on GitHub. I hope you liked this video, and thanks for watching.